Hi guys, welcome back. Now we're looking at section 1.2, graphs of functions. A couple of basic ideas that I want you guys to really focus on. The first one on this note is that points, those are your ordered pairs, points on a graph represent solutions to an equation. Okay, so points are solutions, solutions are points. That's what the graphs do. They represent all solutions to an equation. So an example, we want to determine if the following points or ordered pairs are on the graph of the function f of x equals 2x squared minus 3x plus 1. So remember, if those points are on the graph, that means those x and y values, those inputs and outputs, must be a solution to the equation. So let's plug them in. If -1 is our x and 6 is our y, then when we plug in a -1 into our equation, we should get 6 as a result. And we do, in fact, get the answer 6. So when we plug in -1, we get 6 as our output. So yes, this point is on the graph of that equation. Now let's try B. So they were giving us a y value of -4, but when we plugged in 2, we actually got a y value of 3. So since these values for x and y are not a solution to that equation, in other words, it doesn't make it equal, then this point is not, no, it is not a point on a graph. So when you're graphing functions, we want what's called a complete graph. So it shows not only the basic shape of the graph, but it has to include certain important points. The first of all, we want the horizontal intercepts. Those are the points where the graph crosses the horizontal axis. We've always called them x-intercepts, but again, we may not be using x. So whatever crosses that horizontal axis. We also have vertical intercepts. And those are the points where the graph crosses the vertical axis. And then we have turning points. And these are the points where the graph changes directions from increasing to decreasing or vice versa. So if I had a graph like this, that would be a turning point, or this would be a turning point, like local maximum and minimum values there. So one example of graphing would be this quadratic here, and they're asking us to graph by plotting points. I know there are a lot of different ways to graph linear equations and quadratic equations. The nice thing about plotting points, and that's like using the old-fashioned XY table, is that this works to find points for any graph, whether it's logarithmic, exponential, a derivative, an antiderivative. We can always plug in values for the input, find the output, and plot them. The only problem with plotting points is we need to have an idea of what the graph should look like, the general overall picture, so we know that we have all of the turning points and the important values. So let's plot some points. We know it's a quadratic. Let's start small. Let's do -2, 0, and 2, and see what kind of values we're looking at. So if I plot these points, let's say a -2, I get a value of 10. So again, that would be f of -2. We plugged in -2. That would give us a 10. If we plugged in a 0, we would get a -12. But if we plugged in a 2, we would get a -26. Well, right away, I know that those y values are kind of all over the place. And we have a quadratic where our first leading term is positive. So I know it's going to open up like this. Well, it's still decreasing from -2 to 0 to 2. So I need to start plugging in more points to the right to see where that graph, you know, because it was like positive and then a negative and a lower negative. I need to kind of figure out how far I need to go to get that full turning point in there. So let's jump down and get maybe a 4. If I plug in a 4, I get a negative 32. Okay, so that's a little bit deeper. If I plug in a 6, I would get a negative 30. Okay, so it's starting to come back up, but I still don't know if 4 is my lowest point. So let's try 5. Ooh, that's also a negative 32. Notice I don't have any labels on there. I mean, I could put X and Y, but I don't have 32 hash marks. So we can go by 2, we can go by 3, we can go by 5 if we want. Let's go by 4s on the Y value. So this would be negative 4, negative 8, negative 12. And then we could also do the X values just in 1s because our X's are going pretty small, so that's fine. So with our X's, we can do 2. So as long as we know what scale you're using to make it fit, you don't always have to go by 1s. And let's go ahead and plot the points that we have. I'll do it in green. We have negative 2 right here and 10. So 8, 12, 10 would be right there in the middle. We have 0 and 12. Oh, sorry, 0, negative 12. I thought that's going in the wrong direction. 0, negative 12. 2, negative 26. So that would be here in the middle. 4, negative 32. We have 6 and 30. So that would be right here. And then 5 and 32 would be right here. So again, we know just from our experience of the parent functions of parabolas that they're symmetrical. So even though this graph is coming down like this, there has to be some turning point there. So if 4 and 5 have the exact same Y value, then 4.5 right there in the middle would give us a negative 32.25, which would be barely right there. And it will start to come back up. Now, we can plug in other values for the 6 and the 8, but again, since we know it's symmetrical, if this point is here at 2, that point should match. This point should match. We know it comes back up this way. Now, it's not impossible, but it does take a lot of effort. The nice thing about 140 is we can also use our graphing calculator. We're going to be using that a lot in college algebra. And if you're continuing on in calculus, you'll be using it there as well. So let's graph that exact same graph using our graphing calculator. So when you're graphing on your graphing calculator, we want to hit this Y equals button. So normally you would be in just a generic screen here, but if you hit the Y equals, then that means we're going to graph some equation. So our equation that we were given was x squared. So down here you see the X button. So we're going to have X, here's a squared button, X squared minus 9x minus 12. And I just wanted to give you guys a hint. There's a difference between this symbol here, your minus, and this symbol here. This is particularly for a negative. So if your equation starts with a negative number in the front, you're going to want to use this button at the bottom. If you use the subtraction button, you're going to get an error, and vice versa. So anytime you have those minus or negatives, always look and make sure that you're using the right button. Once you have this in, we can come over here to the graph button, hit graph. But because we know we're using a quadratic, and that it should graph a parabola, we know that there should be at least a turning point in here. That means our window is not the right size. The default for the window, if you hit the window button here, notice it goes from a minimum X value of -10 to a max of 10 with a scale of 1. And then a Y min of -10 to a max scale of 10, but with a scale of 1. It means our hash marks are in ones. Since we graphed it by hand, we can change our scales and change our size. We know that it went all the way down to 32.5 for the Y value. So we can change our X min to a negative. Again, that's why we're going to use this sign down here, a -5. And then X max maybe to a 15, and we can keep it in ones. But our Y min, we know it went all the way down to a -32, but you want to go past that largest or smallest number. So let's go to say a -35. And with an Y max of, I mean, we can keep it 10 if we want to. Now, I'm going to keep it as a scale of 1 just for a second, just so you can kind of see what it looks like. So if we don't worry about the resolution or the trace steps or anything right now. So if we hit graph, notice we now kind of get the full picture. Oh, and we actually centered it pretty well, -5 to 15. But notice all the little 1 hash marks on our Y. That's why it looks a little bit different from ours, is because it's still in a scale of 1. That's fine. If we change the Y scale, if we change the Y scale to, let's say, I think 4 is what we used on our graph, then the picture still looks roughly the same. It's just our hash marks here are nice and evenly spaced and a little bit easier to read. But they don't label it here. You'd have to go to your window to know exactly what the scale is. So you need to label it on yours. So now let's take a look at interpreting some of these functions. I know we did a little bit in 1.1. So suppose we have n of t equals 100t squared minus 5t, 100 units of a product are produced t years after 2005. So again, it's nice to write down what each of the input variables and output variables represent. So the n represents number of products in hundreds. So if n was 7, that means 700. So that's what it means by 100 units. It could be in thousands or millions. And then it says t years after 2005. So t is years since 2005. So if t was 0, that would be 2005. They want us to find and interpret n of 3. So again, that 3 is representing that t value. So we're going to plug in 3 everywhere there's a t. So we get 885. So we need to figure out what both of these mean. So again, the 3 is our t, the result is our n. So that means we had 885 units, okay? So if it's 100 units, that just means we're gonna add 2 zeros onto that. T is 3, so it's 3 years after 2005, which gives us 2008. So we would say in 2008, 88500. So that means 88,500 products were produced. Make that comma a little bit bigger so you don't think it's just one huge number. Then it asks how many units were produced in 2020. Well, in order to determine n, if they're saying how many units, they're asking us to find n, they have to be giving us t. In order to solve for one variable, you have to have the value for the other variable. So they're asking us for N, they are giving us T. Well, 2020 is 15 years after 2005. So T is 15. So they're asking us to find N of 15. So let's plug 15 into the N equation. See what we get. We get 22,425. So we have found the number of units and we know the year. So always, if you can, put it in a complete sentence if they give you a scenario. So we know in 2020, the number of products produced was, and again, it's in hundreds. So you have to add those 2 extra zeros on the end. And then you can put in your count, put in your commas, was 2,242,500 products. I wrote it slightly differently just so the date and the number weren't side by side like I did in part A. Both of them are valid. The very last page is just a copy of the library of parent functions, what a linear, a quadratic, a cubic, an absolute value, a square root, a rational function. So you kind of know what those generic shapes are. So when you go to graph them, you have an idea of turning points or sharp edges or what you might encounter when you're graphing them. All right, that's it. Have fun. Call me if you need me. See you soon.